that was the only solution, how hard would that be in terms of like IMO?
I think that would be quite hard, yeah. But it depends on the sort of the meta a little bit, you know. If everyone's got that on the top of their head, you know.
True. They definitely couldn't put it as IMO one if that was the.
Yeah, can you join the
Oh,
stream as well?
all right. Did it make it look like
Right.
you have more viewers?
Well, I just want to see if it's working as well because that's not the stream. That's the stream. It's always not going to be very many viewers, but yeah. So I should probably state the problem again because the problem.
Yeah.
So I want to say show there are um infinitely many n, yeah, such that this is like 1, such that n equals, say, 2 mod 7, and n to the 4 has a divisor between n squared plus 1 and... Did it include 2n or not? I don't think it did, right? Or we just proved that it didn't.
We proved it didn't. It doesn't include two.
Okay, it's n squared plus... let's just say it's 2n anyway, yeah? Was that the original problem statement? Roughly? Like this part of it?
But that's
Yeah, I think...
wait. Should there infinitely and it's one, two, 5, 6, 7 mod 7,
Yeah.
and that there are not be many.
Yeah, like this is only for 2, but it would also be like 1, 0, 3... 1 through 0, 3, 2, and 6, and 5, yeah. Yeah, I guess one
Yeah.
reason I want you to join is so you can also monitor the chat, because I kind of missed the chat last time. Yeah.
No one else is watching.
Press like.
Yes, sir.
Oh, Justin, we're live streaming. Apparently I have 1,000 subscribers now. But I think they're all for Roblox, so... Yeah. If you want to
Should
join the
we
stream.
advertise your live stream?
So we used to do this like unlisted live stream. One of the good things about the live stream is like you can rewind parts of the lesson, or you can fast forward if you're behind, or you can run it at like 2x speed and stuff. Yeah. So the question is, Justin, have you tried this problem? Show there are infinitely many n. Well, it's kind of like n7 in the prep problem, the part B of n7. Okay. As long as you have looked at it, I can basically just start. Um, have you looked at it? Okay. Where is the chat?
You can see my hello.
Yeah, it's good. I hope number
Oh, there are
3
two,
node rejoins. Huh?
there are two viewers.
I think it's lagged. I don't know. Is Justin in the live stream? Yeah, maybe we can try to timestamp it, but it's kind of live, so it's like it's kind of hard to timestamp it.
You should check who was watching your video, your live stream. Can you check?
I was just on that stream. I was like in that menu. Like it has 2 concurrent viewers, which I assume is just you and Justin, yeah? But Number Theory Nerd joined for a bit, but he might have thought the stream was over.
Oh,
Okay, there was a bit of waiting room. I just disabled waiting room. Okay. Okay, so um I don't know. I just feel like this is I haven't really looked at the question directly the same way, but I feel like this is such an interesting solution that it should motivate our whole lesson. Um so Justin, you can hear me, right? Liam, you can definitely hear me.
can hear you, sir.
Yeah, so this was one of these ideas that kind of just kind of randomly came up. So if you have like n equals so you notice that it can't work if n is prime, right? Um like if n is prime, the only divisors of p to the 4 is like p squared and stuff, right? So n is not prime. We had this idea that if n was composite, so n equals like a times b, you know? Or maybe, yeah, I guess this is fine. Um,
Recording in progress.
okay, so if you have n equals a times b, n to the 4 equals a to the 4 times b to the 4, and n squared equals a squared times b squared.
You have 4 people watching, sir, and there's someone saying, "Show me an induction proof."
Show you an induction proof. What?
Yeah, check the chat.
Alright, let me check the chat for a second. Oh, show me an induction proof. Okay, I don't think. Are they like saying that independently of what we're saying, or are they saying it for this question?
Well, for this question, maybe. For us, then.
If they just joined, they might have missed the question. I don't know. Look at the question first, Penguin. Who is Penguin anyway? Let us know in the chat. Thank you for your comments in the live chat. Okay. So one idea that we had was like you kind of like switch out. You switch out one of the factors. So because you want it to be bigger than n squared, right? But it can't be n squared. And sort of if you imagine these were kind of primes, the sort of the smallest tweak you could do would be like n squared equals, you take away one of the a's and you add in another b, right? Okay, and then the difference between this number, so this is clearly a divisor of n to the 4, right? So the difference between this number and n squared is the ratio anyway is B on A, right? Okay, so you kind of need um oh, sorry, the ratio between, hold on, what am I saying here? So n squared plus 2n. So we need it to be less than n squared plus 2n. So n squared, so a squared b squared. Plus 2ab, I guess. I feel like something different than what I did last time. Okay, so ab cubed has to be less than that.
Different from what we did last time.
Is it different?
Because wait, but D, why is D equal to AB cubed? Because didn't last time we had the N, wait, we had what?
Oh, wait, we just need
N
ab squared, is
squared
that what you're saying?
plus something, and then we had D was what you factor out of N squared plus the thing, right? And it had to have the maximal prime divisor, or at least one.
Oh, yeah. So it was d like b squared or something, and it was n squared plus b squared. No, that doesn't make sense. Hold
Wait,
on.
D wasn't that. There was some other. The N squared plus whatever A.
Hmm.
D was the GCD of both of them, wasn't it?
Oh yeah, but I'm not using that notation, yeah. I'm
Oh,
using d as the divisor of n to the 4.
all right.
Yeah, so something, so if n squared, when we swap out the factors, wait, I feel like we deleted the it was like we have two primes and we deleted the first prime and we added it to the second prime, right? And now I'm a bit confused. What was it on the whiteboard here?
Someone else asked you a question. They just watched your Geometry Revisited playlist.
Oh, nice.
They asked if there's anything else you'd recommend. Should recommend Egmo.
Mm, I don't know, like depends on
Definitely
what the age group is, I guess. Because yeah,
the Geometry Revisited, that's pretty high level, isn't it? Or high enough.
I think it goes a bit slower. It's kind of a nice pace.
Yeah.
Whereas I guess Egmo goes straight into the problems. I guess it depends on
Yeah.
how patient you are. I'm kind of just trying to work this out right now. I'll attend to the chat in a bit, but so yeah, what are we trying to do here? So I remember we had like n was like has like a prime factorization, right? P1, P2 up to PK. N squared was like that. What do we actually add to the n squared? Something less than 2n, right? Something less than 2n. So maybe it was like this. So n squared equals p1 squared, p2 squared, pk squared. And we need a divisor that's like less than n squared plus 2n, right? Maybe, yeah, maybe the letter D is confusing. Make it capital D then, okay?
There's saying more stuff in the chat.
Huh?
More stuff is being said in the chat.
Oh, okay. Oh, these guys are all from Australia.
You guys from India.
Yeah, by the way, do you guys know what the problem actually is? It's actually on the screen in the red. Yeah, at 16:15 on the thing even. It's displayed for some reason. Let's look at the problem statement. Okay. I'll try to get this done because once I get through this, like there'll be a lot of stuff for people to do, even if I'm not saying stuff directly to you. So if we can get this, we should be able to leverage our time better. Okay. So we're on a divisor of n to the 4. So we have n squared plus something, okay? So p1 squared up to pk squared plus, and it has to be something less than 2n, right? So we have, let's say, p2 all the way up to pk squared. I'm pretty sure that's what we had. Yeah, and for this to be less than 2n, we just need pk over p1 to be less than 2, right? And then, okay, so that's not as easy to do as you might think, but okay, let's see where this is. To test, we're going to test that d divides n to the 4, right? So d is actually equal to p2 up to pk minus 1 pk squared. Okay, and this is p1 squared, and then it's p2 up to pk minus 1, and then that's just plus 1, right? Okay, and this is supposed to divide n to the 4, which is p1 to the 4, 2 to the 4. So this is more like motivation for this problem, okay? Once we get to the sort of a solution to this problem, we'll have motivation for the lesson, like the theory. We want to cover some theory. Okay, so if that divides that, it doesn't really tell us anything about, so really just focus on this bit here, okay? So this bit kind of just cancels with a bunch of stuff here. This is pk minus 1, 3, and this becomes a 2. Okay. Okay, and then we see this thing here is co-prime. Is co-prime to, because it's plus 1, right? It's co-prime to all of the p's up to k minus 1. So it essentially has to divide the pk squared, okay? So this p1 squared, p2, the pk minus 1 actually divides pk squared. Okay. And if you kind of think about it, like if pk over p1 is less than 2, okay, like there's not really much room for pk, like p1 squared to sit inside of pk squared, okay? So, you know, for this to really happen, like this thing all has to be less than 4, right? And you're pretty much looking at the condition that pk squared equals p1 squared times p2 times pk minus 1. Okay. So here's the nice thing. Plus 1, sorry, there's a plus 1. Okay, so here's a nice thing about this. We never really used that they were all prime, yeah? So if we kind of just, if we can set this up, we don't actually need them to be prime, okay? So, yeah, but, for example, yeah, if you didn't have this stuff, I think you'd be unsuccessful, because it's hard to find a square that's just one above the prime, right? So that's like, yeah, so if you're doing small cases for this problem, like you'll find, you know, n equals like 2 or 6 work or something like that. So, but otherwise, you're not going to get infinitely many anything like that. But this really helps, because you can essentially have 2 or 3 here, and it'll still be like, it'll still satisfy this condition of being less than 2. Okay. And it doesn't really, we didn't really use that p1 and pk were that prime. Like, if we can just get them co-prime to each other, okay, then that should work as well. So okay, so now that's back to our example. What is our example should be then? Now that I refreshed. So the example should be, so we use 2, okay. So we're trying to get the divisor to be, so d equals, so we put sort of 2 in the middle here. And this will be n squared, so it's 2 squared a squared b squared plus, and this is where we put in the 2, we swap out the 2, instead of ab we just make it b squared. Okay, so it's just like this. We took out the p1 here and made it a pk squared. And so this is our d. Okay. So for this d to work, we need b over a to be less than 2. Okay. And we also want that b squared equals 2a squared plus 1. Okay. Okay. So the question becomes, can we find integers, so a and b integers, or natural numbers, such that b squared equals 2a squared plus 1, okay, and then b over a is less than 2, okay. So you're thinking about it, and it's not necessarily as like if it's just a squared plus 1, you can't really do it. But if it's 2a squared plus 1, there's a bit of room there, right? Like they're at least both going to be odd. Okay. And yeah, so but the funny thing is, if you've kind of done something like this before, you may recognize. So I don't know, you might give yourself like 30 seconds to see if you recognize this equation. But this equation is actually known as Pell's equation. Okay. It's kind of funny. And then, yeah, one of the kind of the first things about Pell's equation is apparently that Pell wasn't the guy to make it up, but it's called Pell's equation. But it's usually written like x squared minus 2y squared equals 1. Okay, so that's maybe a more familiar form for Pell's equation. And yeah, so I guess maybe what I want the lesson to be is like sort of I wanna look at the solutions to Pell's equation, the theoretical ones, and with reference to maybe this book by Dolds, a little bit with a reference to this book by Dolds. I think it's Dolds. We'll see if it's really the name Dolds. But first, I'll give you a solution for this special case, as in like an example of what kind of results to expect. Okay. Obviously, we're not going to learn everything in the absolute sense. We're going to have to assume some things along the way, but we can focus on those things one at a time as well, if it comes to it. Okay. Actually, we do a bunch of those things in our holiday classes. Like, okay, so x squared minus 2y squared equals 1. Yeah, so one of the famous ways of solving this equation is using continued fractions. Okay, and that's essentially what this book is about, continued fractions. So now I can answer the other question. I mean, there was a question about whether geometry, what other books can you self-study for Maths Olympiad? Well, see, even Geometry Revisited, you can't say it's specifically for Math Olympiad, but that whole book series, like it's called the New Mathematical Library. Like, it's getting a bit old now, but the point of that whole series was that it was like actually like written by serious mathematicians for high school students. Okay, and in the case of Geometry Revisited, it happened to be just written, also co-authored by someone from the, like the US IMO team leader. Okay. But there's lots of other books there that are quite interesting. Like this one, Dold's thing for continued fractions. I mean, I would definitely recommend it for Olympiad students. And yeah, and you just got to be aware, like a lot of it isn't really about learning the specific content. It's more about expanding your mind to be able to deal with those concepts and maybe come up with the ideas yourself. Alright, continued fractions. So what we do, so we take this 2, okay, and we find what's called the continued fraction for root 2, okay? So root 2, what does it mean to have a continued fraction? Okay, so you kind of write it like this. You write root 2 is like 1.1 something, 1 point, yeah. People still following? I guess. Hopefully people are still following.
Yes, sir.
Okay, I know. People probably... Hmm. So root 2 is like 1.14 something, right? So this is 1. I feel like I remember showing continued fractions to Justin when you were like in year 4 or something, or year 3, I don't know, I can't remember. So you do 1 plus, and you want to write this, so this thing, so it's meant to be the biggest integer part, and this thing is meant to be less than 1. If it's less than 1, then it should be 1 over something which is bigger than 1, right? So it's 1 over 1 over root 2 minus 1. And because this thing here is bigger than 1, you can just continue it. Okay. And you continue it. So you rationalize the denominator. You get root 2 plus 1. Okay, but root 2 plus 1, the integer part is 2. So we write that as 2 plus root 2 minus 1. Yeah. And now this thing is smaller than 1 again, and we can keep going. This is root 2 plus 1 again. Okay, if it repeats like that, so that's equal to this, then the continued fraction will just repeat as well. So it's equal to 1 on 2 plus 1 on 2 plus 1 on 2 plus 1 on 2. And you just keep going forever. So another way to write that is 1, 2, repeater, brackets. Yeah. Okay. Any questions in the chat? No. Okay, so then what we do is we form these kind of, so this is like our, we form these fractions, like the fractions, these p over q's. Okay, so for example, I think, so p1 over q1 will just be continued fraction, it stops at 1. And pn, or pk over qk, so it just stops at k. So this is just 1, and we kind of individually get the p's and the q's. So p2 over q2 equals 1 and 2, which is 3 over 2. And p3 over q3 is 1, 2, 2. Which is it's 1 plus a half, 1 plus like this, yeah, which is 2 over 5 plus 1, which is 7 over 5. And you just keep doing this. So there's actually a faster way to get these numbers, but we should do it this way once in our lives. That's what they say. Yeah. So this is 1 plus 1 over 2 plus 1 over 2. So this is 2 on 5. 12 on 5, 5 on 12, 17 on 12. Okay, if you want a quick way to get the numbers, so these, the numerators are the p's and the denominators are the q's when they co-prime. So if you want the quick way to get the numbers, you basically see that 7 equals 2 times 3 plus 1, right? 5 equals 2 times 1 plus 1. 17 equals 2 times 7 plus 3. 12 equals 2 times 5 plus 2, okay? So basically, Why is it 2 times something plus 1? Plus one of the next thing. It's this number here. Okay. So it's meant to be Pn plus 2 equals a am plus 2 Pn plus 1 plus Pn. And it's the same for Q, okay?
I think all your viewers left.
Yeah. It's strange though, the earlier part should be the easiest part. Or maybe they never thought about the problem, so they didn't know what we're talking about. I think one of those people in the chat was actually Little Michael.
But which one?
I think it's a random child.
Oh.
Or maybe it's someone else. I don't know. So, yeah. Yeah, so you guys with me so far here? So, the point is that all of these fractions, okay, they're gonna get closer and closer to root 2, okay? So Pn on Qn approaches root 2. Okay. So in particular, the fractions are usually going to be less than 2, okay? And half of them satisfy Pell's equation, and the other half equals -1, okay? So, let me say this. So the good thing about the example is you don't have to prove it. It kind of exhibits itself. So like you do like 3 squared minus 2 times 2 squared, right? That's equal to 1. 1 squared minus 2 times 1 squared. That's equal to -1. 7 squared minus 2 times 5 squared. That's equal to what? 17 squared minus 2 times 12 squared. Okay, so obviously this is -1. This is 1. Okay. So for 2, it should always just alternate between 1 and -1. Okay. Okay. So if you want to just kind of look at the numerators and denominators. So for example, you get So this is like P, this is Q. You get 1, so it starts on 1 on 1, and then it's 3 on 2, right? Let's do it mod 7. And this is plus or minus. Let's say this is a minus. It starts off with a -1, right? And this is a plus. So you do 7, it's just 0, mod 7. This is 5, mod 7. 2 times 0 plus 3 is 3. 2 times 5 plus 2. 5 is just -2, yeah? So it should be still 5 again. 1 times... So 2 times 3 plus 0 is 6. Oh, that's weird. I don't remember there being a 6. Okay, 2 times 5 plus 5 should be a 1, right? Yeah, it's 3 times 5 is 1. And 2 times 6, 6 is -1 plus 3, so it's just 1 again. What? Minus, plus, minus. Wait, have I made a mistake? I'm just doing 2 times the previous number plus the previous number before that. 6 is -1. -2 plus 3 is +1. '21, 12, 15, that's 1. 2 times 1 plus 5 is 0. Okay, so it should repeat, right? Like mod 7. 2 times 1, this is 1 again. 2 times 0 plus 1 is 1. 2 times 1 plus 1 is 3. This is 2. Okay, can you see it just repeats from then on? So it should be this thing. Repeated. And it should be these things. Yeah, that's kind of weird. So the number itself, so this is our like A and B, This is like B, this is A. You have N equals 2AB, So it should equal, so here it's 6. 6 times 2 is 5, yeah? That's 1 times 2 is 2. Okay, I think I'm in business. 0 times anything is just 0, yeah? Okay, so what we showed was that using this approach, that there are infinitely many n which are 2, 5, and 0 mod 7, you know? So we got 2, 5, and 0. So the question is, what about 1, 6, yeah? And 3, 4. Okay, do you guys understand what just happened? Does that make sense? Like a poll. Oh, did you guys both quit the stream? Are you guys still in the stream or in the Zoom? Ah, okay. Yeah, hopefully that'll be better. I'll be back. My flight's actually tonight, so I won't have to do this backup internet kind of thing, hopefully, after today. Okay, so the activity is, so do you guys know what the activity naturally is from here? Can you guess what the activity is? Okay, there's a bit of silence here. I mean,
Hello, sir.
can you guess what the
But do we
activity is?
find solutions?
Find solutions for what?
The Pell's equation? Or not solutions, solutions mod 7.
Okay, and then what? How can we do that though?
Go through the continued fraction.
Of what?
But the two possible things were root 2 and root 3, right?
Yeah.
Yeah, go through the continued fractions of root 2 and root 3.
Okay, but we already did the continued fraction of root 2, right?
Yeah, now you have to do the one for root 3.
Yeah. Okay, you understood what happened for root 2, right?
Yeah.
Okay, so the activity now is to see what happens for root 3. Because the reason, because remember, this could be 2 or 3, you know? Like, we could fit 3 there and it'd still be less than 4, you know? Does that make sense? Okay, so can you can you guys get started on doing it for 3? I'll join you in a little bit, but I feel like I need to get some hands-on stuff. Root 3. Yeah, do you guys know what to do? So try to see what happens with root 3. Can we get the other mod 7s or not? Okay. So I'm interested in this as well because I haven't done it. I've only done the root 2. And I was looking forward to doing the root 3 with you guys together. Okay. But there are some steps that hopefully you should be able to do, but it might be a bit slower since you've never done this before. Hmm. Okay, so I'll just give you guys a head start, but I'll start at some point too. People shouldn't be stuck yet, right? So the question is, are you guys writing something on paper and stuff, or are you just waiting? If you're doing stuff, say yes. If you're just waiting, say no. Okay, good, you're doing stuff. Excellent. So it's not an awkward silence. It's a productive, meaningful silence. Wait, did we get one? What we get 1 and 3 repeater for the continued fraction? Is that what you guys got? Hmm. Something's not quite right. Something strange here. 169 minus 300. 131. Hmm. Oh wait, was I doing? It's just 3 plus 1 equals. Right, I just need to go to the toilet for a sec. But can you guys check if we have the same thing so far? Alright, I'm back. DM, did you get the same answer so far? Where is the Liam?
Kind of got stuck on the continued fraction.
I'm wondering if I got the right continued fraction now. I should have done a few more steps. But did you get the same numbers as me or something else? Hello? Are you talking? Because I can't hear you say anything. Okay, I think I might have done the continued fraction wrong then. Let's have a look. So root 3 equals 1.7 something, right? Plus 1 on root 3 minus 1. So root 3 plus 1 is 3 minus 1. Root 3 plus 1 on 2. Okay, so 1.7 something, 2.7 something over 2 is like 1.3 something. So it should be... Oh, why did I write a 1? I wrote a 3 when it should be a 1. Huh? Yeah, I think I wrote the wrong thing. Should be a 1 plus root 3 minus 1 on 2. Alright. It was 1 plus 1 over 1 over 2 on... Okay, I missed the 1 at the start, I think. Root 3 minus 1 times root 3 plus 1. So basically this cancels with the 2. Yeah, okay, that's what I forgot the 1 over. It was like a typo. So this should be 1 over root 3 plus 1. So then it should be 1 plus 1 over 1 over 2 plus 1 on 1 over root 3 minus 1. And then it should start again, you know? So it should be like 1. Is it like 1, 1, 2 repeater like this? Okay, well you could have corrected me before when I said this. I asked about this. Could have saved us some time. Okay, though it is my responsibility to check my own work. Okay, so 1, 1, 2. So then the P's and Q's become yeah. Okay, so we do P over Q. So the fraction is like 1 plus 1 over 1 plus 2 plus 1 over 1 plus 1. Okay, so P, the first one is just 1 over 1. The second one is actually just 2 over 1. What the? The third one should be 7 over 4. Is that right? 3 over 2, 2 over... What? No, that's not right. Sorry, I did the wrong thing again. The next one should be 2. So this should be 5 over 3. So it's 3 over 2, 2 over 3, 5 over 3. Yeah. The next one should be 7 over 4. 7 over 4. 1 over 3, 4 over 3, 3 over 4, 7 over 4. It is, yeah. And then you do 2 times 7 plus 4. So 14, 19, 8 is 11. And then you just add them up. Get 26 over 15. Is this what you guys got for P over Q's, like the first couple?
Yeah.
Is that what you got? Yeah, so the reason I thought my thing was wrong is because they didn't have anything to do with Pell's equation. So hopefully this will have more to do with Pell's equation. So still 1 squared minus 3 is not good. Minus 2. 2 squared minus 3 times 1 squared. That is a solution. Okay.
We got that solution before. So this is already showing it's promising.
Yeah. So 5 squared minus 3 times 3 squared equals what? 25 minus 27.
Minus
7 squared minus 3 times 4 squared is what? Oh.
I think that's a pattern. Seems to be a pattern.
Yeah, 19 squared minus 3 times 11 squared equals what? So 361 minus 3 times 121 is 363. Seems to be
3
alternating between minus 2.
and 1.
Yeah, why is that, huh? Consistently minus 2 or 1, huh?
Yeah.
That's very strange. Actually, I'd like to know what's exactly known about continued fractions, because I feel like there's still probably a few open problems, you know? Maybe quite a lot. I don't know. So, what is that? 220. What's 26 squared? 6 plus 50 plus 676. That's 3 times 225. 676. 675. Oh, look at that. It's a
Yeah.
solution. So maybe every second one is a solution, huh?
Yeah.
Okay. I wonder if we actually can conclude anything from this. So if we take it mod 7, what do we get? 1, 1, 2, 1, 5, 3, 0, 4, 5, 4, 5, 1. I'm trying to remember, what is this? This is just 2, 2. Just add them up. 2 times 5 plus 2 times 5 plus 5 is 1, right? That's 6. And here, 6. 2 times 6 plus 1 should be just 6. Let's see. 4 plus 4 is 1, yeah. 2 times 1 plus 4 is 6. 6 plus 1 is 7. 2 times 0 plus 6 is 6. It has not repeated yet. What are we even up to here? 6 times 6, 6 plus 6 is 12, which is 5. 6. 2 times 5 plus 6 It's 2. What? 2 times 5 plus 6 is 2, huh? Then 0 again. How's Justin doing? Is your stuff agreeing? 5, 6. Hmm. Just add those up. Okay. 2 is 18, that's 4. And then just add them up, you get 3. Hmm. Yeah, 2 times that is 3. Is 2. Okay, now we're getting like the negatives of all the stuff here, yeah? So it's gonna start repeating. Hmm. It should be negative of everything now. So the next one should be like a 2 as well. The other one should be a 1. Yeah. What? It's a 6. That's a 2. 6. Like it should go all the way to the negatives of this. Yeah, but if it's negative, I mean, negative times a negative is positive. So it should give you the same products. So let's see if we can just. But the question is it even or odd? Where does it actually start repeating? It looks like it starts repeating even here. That's where it starts repeating. This is all just a negative of that. And our solutions are here, 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 here. And so it is consistent. It
The
doesn't,
solutions are the negatives, though. Oh, wait, yeah, it's consistent.
yeah, it matches up. So you don't get anything new, yeah?
You don't.
Which makes sense, right? Because when you square it, it's like the same. Okay, so what numbers do we get then? So we get 0 again, right?
502.
We get 0 here, yeah?
Yeah, 5 and 2.
Oh, it's not quite 5 and 2, right? What is it?
Oh, yeah. We need to square them, right?
No, no, no. You want the n in the original problem. Remember what the original n was?
What? P squared times Q squared?
Yeah, that's n. That's no. That's nothing. That's not. Yeah, that's kind of related to n squared, but it's not.
How's n defined again according to these?
Remember the a and the b? The a and the b are the p and the q.
Wait. A times B equals n, right?
No, that is the
But
catch.
what equals n?
Try to remember. Hmm? Yeah, do you remember what it was?
No.
Wait, where's Justin?
Excellent question.
Come on, try to remember, because this matters for this problem at least. Oh, Justin, do you have the same numbers as we got so far? Okay, so what's n then? Yeah, Liam.
Don't think I remember.
But it's not just remember or not remember. Like it's a process of relating things together. Like how did we even do this in the first place? How did it work for 2? Do you remember?
My memory's not working the best today.
Remember, like the whole point of it was like we stuffed in like it was like p2 up to pk minus 1. That stuff in the middle, right? We stuffed the
Yeah.
2. We stuffed the 2 into that to make it like a squared equals 2 times b squared plus 1, right?
Now I remember.
Yeah. So what is it?
Pretty sure it's 6 and 1.
Yeah, good. Okay, so n is equal to 3 times ab, right? Or pq. Yeah.
Yeah. So it's 6 and 1. Or no, yeah.
So this is 6, and this is 1, right? Which kind of works out perfectly for us, right?
Yeah.
Because
I think that's all.
that's literally a part b solved, yeah?
Yeah. Now we just need to show that these are all the solutions. Or not.
Or whatever, I don't know. I'm not really focused on part a for now.
Right.
But notice how we got 1 and 6 now, yeah?
Yeah.
I don't know, like it's kind of a surprise because I never expect, like it's not, I don't think, I don't know, like, yeah, the problems are 5 years behind, right? But, like, given the difficulty level you'd expect from that, like, N7 per problem, you wouldn't think this is the intended solution, um, but it's pretty cool nonetheless, right?
Yeah, it's a very nice solution. But yeah, it does not seem like the intended. The intended solution, they probably use the mod 7 to reduce it into a simpler problem.
Hmm. Okay, so then do the next bit of theory, okay? So we're trying to figure out how to solve Hell's equations, okay? So this is going to be a bit, hopefully that'll motivate you for the kind of, the less action-packed. I mean, it'll be action-packed, but it's not the same as number crunching action, you know?
Yeah.
Recording stopped. Recording in progress.
Okay, so there are some facts that we might want to assume for this exercise, but we kind of just, what we want to do, like the goal of, I guess we only have like an hour left. I actually have to check out of here and leave in like 2 hours. But at least in the next hour, the goal should be to check that the continued fractions for root n solve solve Pell's equation. Solve the Pell's equation for n. Somehow, okay? Yeah. Yeah, I guess you can solve part A if you kind of show like they have to be solutions to Pell's equation or something, you know what I mean? Which maybe this theory will help with, but I think this is interesting enough now even without caring about the problem. Let's have a look what we have in the notes. So there's some things we want to assume, okay? So the kind of things we want to assume are like, you know, that the P over Q's are given by those formulas, okay? And let me just put it here. Let me at the bottom. Okay, so we need to come up with a statement as well. So the kind of thing we want to assume is like, we actually assume we know what the continued fraction for root n is, okay? And this is related to what we did last time, showing that it's basically it's a quadratic irrational, and if you add something, it'll be reduced, okay? But I think for the sake of this exercise, it might be good just to assume what it is, okay? So basically, like, if you added a1 to it, it would repeat completely. But at the moment, it's only this part that repeats, so it's a2, a3. And then the only special feature about the a2, a3 is that it kind of climbs up and then it comes back down. So it goes back down to a3, a2. So it kind of goes up the middle. The middle is like the highest, and then it kind of starts repeating back down to a2. Okay. I guess you don't really see that much with, yeah, like you didn't really see it much with root 2 because it just kind of started repeating right away. So root 2 would have had like just a1 and there was no a2, okay? Root 3, I think it would have had a1 and a2, but there was no a3, okay? Yeah. Okay, and then there's this kind of these kind of lemmas with the p's and the q's. Not sure if we probably don't need all of them, but I think the basic ones it really helps to know, like how the recurrence is defined for the p's and the q's. Okay, and there is one that really helps for us is if you basically if you have you know, if you cut the fraction at some point, you have just like Pn plus 2 over Qn plus 2. Okay, then that naturally equals An plus 2 Pn plus 1 plus Pn over An plus 2 Pn plus 1 Qn plus 1 plus Qn. Okay, and so that's what happens if it's like a finite fraction, right? And so there's this other thing which is kind of helpful, is like if you write the fraction, like if you write it like like A1, A2, but you stop it like at AN, and then instead of keep on going, you terminate it with alpha n plus 1. Okay, so now the alpha is no longer an integer, but it represents like all of the stuff. Like it kind of goes 1 on alpha at the end. Okay, but it kind of terminates. Okay, and so basically then what you get is the x itself is equal to the alpha n plus 1 times p, this is pn plus pn minus 1 on alpha n plus 1 qn plus qn minus 1. Okay, that's kind of like a way to really manipulate this notation. Alright, I think that's all we really need. Okay, so, and if we need anything else, that might be interesting as well, because all I seem to remember, so the things I remember about continued fractions are basically like this thing here, and the recurrence relations. Okay, and if we know the continued fraction for root n, it should be enough. Okay, so let's see what we can do with this. So if you assume that's the continued fraction for root n, how can we show stuff is a solution to Pell's equations? Okay, we should probably try a lot of this ourselves for at least 10 or 15 minutes, and then we can maybe look at the book as well to see what they do. I think I originally saw this from the book anyway, so I think the first step should be pretty obvious. Like, basically, you try to use the fact that it's kind of repeating to try to solve the n. So maybe let's call this Pn over Qn. Wait, this is maybe n plus 1 or something. This is like Pn plus 1 over Qn plus 1 if you don't have the repeater. And if you repeat it one more time, I think it's P2n plus 1 over Q2n plus 1, right? Yeah. Yeah, so root n minus a1 equals this repeating thing, yeah? Equals a2 yeah, Yeah, so it's kind of like when it's like that, even like the AIMO question with the decimals, it's kind of like that, right? We just got to kind of take advantage of this repeater thing. So people say the continued fractions are more natural than decimals because, well, because for rational numbers, the decimals repeat, whereas the continued fractions terminate. And it's only for irrational numbers that it starts not terminating, and the repeating happens for sort of, maybe you can consider them the simplest type of irrational numbers. So how do we do this repeating thing? So maybe this is like, A2 all the way up to A2 to A1, and then this is like your alpha. And then it terminates, and your alpha is actually equal to root n minus A1. So root n minus A1 equals, that's a fraction, root a n minus A1 times Pn plus 1, let's say that's Pn plus 1, plus Pn on Qn plus 1 root n minus A1 plus Qn. Yeah. Let's see. So we'll just proceed naturally, yeah? How to get rid of the root n's in the end? Let's see. Oh, okay, I think I remember now. So it's kind of like you just times it all out, right? And then you get a relation between the p's and the q's. Okay, let's have a look. Are you guys still with me? Okay, good. Yeah, it's funny, the online, the stream people are probably they come for like 5 minutes and leave. It's all about intention, I guess. Okay, so if you have that, so how do you expand that? Let me write, so this is Pn, so on the right hand side is Pn minus a1 pn plus 1 plus pn plus 1 root n, right? On the left hand side, I have to write this a bit weirder. It's like this times that, yeah? So there's like qn plus 1 times n. There's qn times a1. And there's the root n stuff. The root n stuff, I guess, is like qn times root n, and minus a1 times root n, and then there's qn plus 1 minus times, so this is minus a1 qn plus 1, and then there should be one more non-root n, right? Wait, how many terms should there be? There should be 1, 2. There should be 6 terms. So 1, 2. We have 5. So there should be another non-root n term. So maybe like an a1 squared or something. a1 squared qn plus 1. No? Okay, this looks like a bit messy, but yeah, so the nice thing about this is everything's an integer, so the root n actually adds another dimension to this equation. So it's really, you get two equations in one here. Okay. Two equations in one. So one of these equations is a n plus what was q n plus 1 n minus q n a1 plus a1 squared q n plus 1 equals pn minus a1 pn plus 1. That seems kind of weird. Okay, and then so what about the root n's, yeah? Then qn minus a1 qn plus 1 equals pn plus 1. Okay, so I guess we have two options. I feel like I'm getting weak in my age, but we can either keep going forwards intrepidly and kind of think about whether this is true or not, or we can kind of check with the book just in case we don't have enough time to fully What do you guys think? A1 QM plus 1. Yeah. I guess one problem is we have here is we haven't really, like, we've taken into account that it repeats, but we haven't taken into account that it like does the palindrome kind of thing. So it feels at the moment this is just saying that it repeats. Yeah, so now I'm kind of a little bit worried because there's like another fact from the palindrome thing that might be quite helpful. Yeah, like so from a previous exercise, we showed that, like, for example, if you do the backwards fraction, like the fraction with all the a's reversed, instead of getting p over q, you get actually just the p over p. Okay. So, so it could be, for example, that, because it's repeating, some of these qn's are actually equal to, or qn plus 1s. Oh, sorry, probably the qn's. Yeah, the qn's might actually be equal to the p somethings. Yeah. Okay. I just want to have one look for 15 minutes. Oh, I restarted, that's right, so... What do we have? Fell's equation. Oh, okay. Maybe that's not maybe a better way to do it. So like if you have this thing repeater here, instead of subtracting the A1 from the other side, you can actually add the A1 and make it 2A1 repeat to AN. That might be better for the sake of getting this AN here. The other thing should still work. Okay, so then you get root n equals alpha n plus 1 pn on qn, yeah. Okay, it's the same as what we did. And then, yeah, see, these things look much simpler. What is it that made them look simpler? Okay, so you have this is the same as what we had, yeah. And alpha n plus 1 is something root n, yeah. Okay. Oh, wait. Maybe we didn't simplify something we could have simplified. Yeah, and that's probably because we had the A1 here. Because their thing, you get the... Wait, there's still also A1. Huh. I'm kind of confused. Why is it so much shorter? To get that, so you get Qn times n, which is what we got, yeah. And here you get A1 times... Oh wait, this one has... Maybe I times... Did I times it wrong? Oh, okay. So the reason that it's different is because I have this extra minus A1 here, which introduces actually another 3 terms. Yeah. Hmm. Okay. Yeah. So maybe we can go from here. It kind of looks nicer, though. It probably would be more illustrative if you struggle with this, but just for the interest of time, let us look at this. Yeah, see the difference between reading it and actually doing it is kind of different, right? Like we're reading it, you'd just never have a second thought about any of this stuff. But there are some choices you could have made if you were trying to actually do this. Okay. So set alpha plus n plus 1 to be essentially the tail. Okay, is this true? So root n is supposed to equal a1, a2, dot, 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 an. Oh, so it doesn't even use the fact that it goes back down the palindrome part, huh? So that's, is that where? So then that's, and then this is called alpha n plus 1. Yep. Yeah, and alpha n plus 1 is the part that repeats. Okay, that looks right. Okay. So root n is the original number, right? So that's the x in that relation we had before. So root n is equal to the tail times the previous one plus the one before that. You know? Okay. So then if you do that, you get these two things, which I basically believe, I mean, so what is it? You have 3 terms equals to 3 terms. And two of them on the left hand side go for the square root, one of them on the right hand side, and then 1 and 2 for the non-square root. Okay. So rewrite these in terms of Qn. This is in terms of Pn minus 1. Yeah. So Pn minus 1 equals nQn minus A1Pn. And Qn minus 1 equals Pn minus A1Qn. Right. That's this. Okay, we're good up to here. Okay, remember we could assume this. I said we can assume that from before. And if you sub it in, what do you get? So if you sub it in, so you're just subbing in this thing here, and this thing here. Okay. And so notice this is the Qn squared, Pn squared, and the other stuff just cancels. Which gives us this. Yeah, so you can see there's a little bit of difference when n is odd and when n is even. So the n is actually where the thing before the 2a1 happens, right? So like in the case of root 2, n was just 1. Was it n was just 1, or I guess maybe n was 0. Right, n was 1. But you could have actually made n anything in root 2, because you could have just said that it was like that and then made 2 the last thing. So you could always pick n to be 2. Okay. So that's the whole point. Like, you might get -1. So it's only talking about the Pn and the Qn, not all the P's and Q's. It's only the one, like, just at the end of the repeat before the 2a1. So it's like that. But of course, you can actually pretend the period is actually twice as long. And you can essentially, I think, double n. You should be able to double n. What can you do? So you have a1 up to an. It's like that. Okay, this has got length n. Yeah, you can essentially add another n minus 1 to the n plus 1. So you can double n. So you can make n, you can make any multiple of n as well as the smallest n. Yeah. So in particular, you can make n even, and that'll be a solution to the Pell's equation. Okay. Alright, so let's take a short break. Maybe just like 1 or 2 minutes, go to the toilet, and then let's see if we can recount this. I can try to type this up. Okay. Um, okay. Give you the link. Um, okay, I just need to go to the toilet for a sec. Alright, we ready? So we have about 20 minutes to do this, okay? So let's see if we can do it. So you guys remember what the statement should be? It's here. So we don't even need the yeah, it's kind of weird to describe this because the 2A1 might just coincidentally be equal to something instead of being the actual 2A1. Hmm. Yeah, so with the period L. Okay, then let n be any multiple of L. Okay. Then Pell's equation x squared minus n squared equals 1 has solution Pn Qn. Hmm. So we should probably define Pn and Qn. But there's a few ways to define it, obviously. You could just define it by the recurrence if you want to be a bit mysterious. Or you can see they can be like the partial quotients or something. This is like pk and qk. Has solution Pn Qn. Okay, so can you remember what the proof was? Um, so, right. So I think we should write it as like our own version, I guess. Square root n as equals, so it's a continued fraction, an, and then we can have alpha n plus 1. So we see that alpha n plus 1, so that's the tail, it's actually 2, it's the 2a1 equals 2a1 dots a2 and that equals the square root n plus a1, yeah. Okay, so then we use the relation. So square root n equals, this is the alpha n plus 1 p n plus p n minus 1. I guess this kind of needs n to be at least 1, okay? So what's p0? I guess we can define p0 to be something like 1 or something. Okay. And the denominator is the same, but with q. And the point is that's equal to that's equal to so alpha n plus 1 is now just root n plus a1, right? I feel like at this point it can be more distracting to include the calculations. I might just say like write like clear denominators and rearrange it to be of the form, yeah. So from here, denominators and rearrange the expression so it is of the form a plus b root n equals c plus d root n, and equate a equals c and b equals d to get after we arrange it. Okay, remember what we actually got? We got like Pn minus 1 equals something, and Qn minus 1 equals something. Can we remember what those somethings actually is? Substitute these into that was Pn Qn minus 1 minus Qn Pn minus 1 equals minus 1 to the n. So if we're substituting these in Pn, so there should be a Pn here, right? Pn. Remember it worked out, so the Qn minus 1 should have a Pn. Okay. There's something that cancels. One is Qn, and the Pn minus 1 should have a n Qn somewhere, right? It should have an n Qn. So the question is, which one was plus, which one was minus? I feel like it was... For some reason I feel like the Qn was plus. Let's have a look. We can quickly check. Yeah, so the root n times this root n will give you the Qn. Okay. And on the other side it's an. So it should be Qn minus a1pn. Okay. So it should be Qn minus... Wait, what did I just do? Yeah, it's a Qn nQn minus a1pn. Yeah. The nQn minus a1 pn. So I guess the exercise is to try not to look at the book again, but nQn minus a1 pn and then this must be plus, oh wait, that's minus a1 qn. No. Okay, and if you look at that, the square root n, there's a, on the left hand side there's an a1 qn, and a Qn minus 1. And on the right hand side there's a Pn. So it should be Pn minus A1 Qn. Yeah. Then you got Pn squared minus Qn squared equals minus 1 to the n. Now take m to be even so that now if L is even, n is even, but if not, then let m be even. Either way, n can be made even, and we get for these even n, yes, obviously for the odd n you get the minus 1 solution, which we got in square root 2, but we never got it with the square root 3. Right? Yeah, so this is actually not quite true here. If n is even, equals minus 1 if odd, we'll have p sub 2l q sub 2l in particular is a solution. So what was it for root 3, right? Root 3 it was like, for root 3 it was like 1 and then 1, 2 repeat, right? So n could be 2 and that's already even. But for root 2 I think n was 1 was not even, but you could make just n a multiple of 1. You just make it 2. So in both cases, every second one, you got a solution. Okay, so I guess one question that I have is, we did not use the palindrome condition on the continued fraction for square root n. can we do more if we take that into account? Okay. Okay. Yeah, so it's clearly infinitely many solutions, right? Um, it doesn't quite say it's all of them. That's not in this statement, but yeah, and I guess. Uh, okay, does that make sense? How well was this understood? The endless poll here. Oh, two decents. Yeah, I think maybe the decent is something related to maybe the discomfort with assuming certain things. Oh, okay. Excellent. Alright, have a good one, Justin. See you. Liam, do you have any questions you want to ask?
Not really. Wait.
Hmm.
Recording stopped.
Wait, I don't think I have sound. Maybe that's what the problem is. Are you saying anything? I can't hear you. Okay, maybe I don't have sound. Okay, well that's pretty much it anyway. Um, do you have any questions? Yeah, so I wonder if the converse is true. Like, if the only way to get a factor of n to the 4 is to kind of remove a prime and add another prime or something.
Or the question.
Like, I feel like the original argument kind of proves that that might be one of the only ways to do it or something. I mean, like if you run through the original argument, instead of having P1 to PK, right? And, um, yeah, you know what I mean? Yeah, like if you set n equals the p1 to the r1 all the way up to pk to the rk, you might be able to do something. I don't know, if you're interested, we can keep doing more stuff online. Yeah, I guess I'll be flying tonight. I should be able to get back before sometime on Tuesday. So I don't know. At the moment, the plan is to have Thursday, Friday be the start. But I feel like if we get earlier, we can maybe do some stuff online. Yeah. Yeah, but let me know how you go with the arguments. Oh no, stuff will happen. But yeah, I gotta check out of this room now, I think. Alright, have a good one.